Snellen chart. Hi, this never ends. Look at that. Now we need to talk about the visual pathway. Because what are we going to do? We're going to have to project this picture that the eyeball picks up, that's called the visual field, onto the cortex, the primary visual cortex, and that's in the occipital lobe. So when we look at the visual field, the whole visual field we see is the whole thing. But then we got a left one and a right one. So let's pick one of those. So we're going to pick the right one. When we look at the rays that come from the right visual field onto the retina, on the right eye, they go to the area of the retina that is the half of the retina that is on the nose side, the nasal side, or the medial side. When we look at the other eyeball, they also picks up this picture, this right visual field, but it picks it up on the outside part of the eyeball, the temporal half of the retina, or the lateral half of the retina. Oh, what I forgot to say is the reason why this discussion is happening, one of the reasons is because we actually have this phenomenal thing of 3D. We can see 3D in real life. In the movies we need glasses, but in real life we could just see 3D. And the reason why we can see 3D is because we pick up the same object with two different eyes, a little bit spaced apart, and that gives us a little bit of a different angle, and we can overlay those pictures in the brain, and then that gives us this depth perception. That's the 3D. So now let's go back to this. So we have this visual field, we have the retina here, and from there the optic nerve comes out, and then it goes to an area that's actually right on top of the sella turcica in the skull. Remember that inside there, a little in front of that big hole that the spinal cord comes out, that one. And right there on top, the nerve, the optic nerves actually cross over. But not the whole optic nerve crosses over, just part of it. Because now what we're going to do is we're going to make so the information that goes to the brain, back of the brain, is coming from, is related not to the eyeball, but to the visual field. So because then we got these two pictures that we can overlay and see 3D. So now we're going to take the lateral field of the eyeball. Those fibers, they don't cross over. They just go straight back to the occiput ultimately. The one that come from the inside, the nasal part though, those fibers, they cross over to then bring their information from the right visual field also to that side of the cortex. Does that make sense? I hope. Otherwise we'll do it in class a little bit more. And of course we're not just going to go straight from the eyeball to the cortex. We're also going to stop at the thalamus. Like every sensory input except for smell will have to more or less stop at the thalamus. So we have a few more terms that come up there. So first of all though, the crossing is called the optic chiasm. And after the optic chiasm, at that point, let's go up here. Then we call that stuff going back to the thalamus, we call that the optic tract. And then from the thalamus into the occipital lobe, we call it the optic radiations. And then we go to the primary visual cortex in the occipital lobe. That's it. Down here it talks about that depth perception. But that's pretty neat, huh? I know. Now what we can do is now we can actually go even further than that. Now we can look at pathology. We can look at lesions along the pathway. We can figure out a little bit where the lesion is. We can figure out what the problem is. So for example, if we have a lesion in the optic nerve, bam, we miss the left eye visual field or the right eye visual field. So we miss the depth perception. We miss information from one eye. We only get the other eye coming in. So we have blindness in one eye. If we have, for example, a pituitary tumor, and the optic chiasm is right there by the sella turcica, so we squeeze the optic chiasm, we only gonna get the transmission of two outside fields, the temporal fields here, the ones that cross over. We get a visual field disturbance in those. So we actually get bitemporal hemianopia, it's called, or tunnel vision. We only see a tunnel. We don't see the periphery, because actually the fibers that cross over pick up a little bit more of the peripheral vision, because the most depth perception we have right in the center of the visual gaze. So that's kind of interesting. And then we can have an injury to the optic radiations, for example, in the back here, the optic radiations, and that leads to a defect in the opposite visual field. So we don't see the other side of the visual field. But anyway, that doesn't need to be all that fully understood. What's kind of cool is we can see where a lesion is depending on what the person can see or cannot see anymore. And that brings me to the accessory organs. Eyebrows are short, coarse hairs overlaying the skull's supraorbital margin. They help shade the eyes, so that's actually a natural sun hat, but they also prevent perspiration from, getting in, the sweat getting into the eyes, and then it stings. So we then need to blink too much. Eyelids cover the eyes anteriorly. There's upper and lower eyelids, and they're strengthened by little connective tissue plates called tarsal plates. Then they all have sebaceous glands in it, and that, of course, every eyelash, every hair that we have has a sebaceous gland feeding into it, so it doesn't dry out. And so we have eyelashes there. Also, another piece that we have, that's the conjunctiva. And the conjunctiva is kind of cool, because conjunctiva is a thin mucous membrane that is on the eyelid, on the inside, but then it folds back at the end and goes over the eyeball. So it's actually covering the whole eyeball as well as both insides of the eyelids. And that's protective. But it can get inflamed. And if it is inflamed, we get what's called pink eye. That's conjunctivitis. And conjunctivitis is very contagious. So when you have it, you stay at home. And that brings me to the lacrimal gland. Let the tears flow. The lacrimal gland lays on the outside here, on the outside of the eyeball. And as we cry, little tears come down, cross the eyeball, and enter into the nose. That's why if you have something in your eye and you get water in the eye, you never rub your hands from the inside out. You always rub it from the outside in to help the flow of the stuff being flushed out across the eyeball. The tears are cool because tears contain mucus and antibodies and also lysozymes, and so they clean and nourish the cornea. They also help us stimulate the release of endorphins. So when we cry, emotionally, it's a very releasing thing, and we feel better afterwards. So guys, please cry once in a while. Oh, coolio. Let's go to the hearing and the equilibrium. When we think of the ear, though, we usually think of organ of hearing, so we can listen to our music. But we also have the organ of balance in there. The inner ear, which is where all that stuff happens, that transduction from sound waves to nerve impulse, but also the balancing out, that all is located in that, remember that hilly part on the inside of the skull called the petrous portion in the temporal bone? That's where it is. So when you see this hill here, that's this part, temporal bone, petrous portion. The external ear and the middle ear conduct sound waves. Sound waves come in here. They vibrate the tympanic membrane. Vibrate. And then the tympanic membrane goes onto 3 ossicles. And then they vibrate here. Right there. And that's the middle ear. Right here. And then from there, we get into the inner ear. And that's where the magic happens. When we look at the outside, the ear part, we have this funnel-shaped auricle, also called a pinna. It's elastic cartilage, so you can bend it and turn it, and it goes right back to the regular shape. So that's kind of cool. The eardrum is known as the tympanic membrane, and that stretches actually over a bony canal. It's kind of cool. It actually doesn't look like this really. It looks more like a small little tiny djembe that you can play drums with. We also have earwax glands. You notice maybe sometimes you have earwax, and we'll take that out. And that's made by ceruminous glands, because earwax actually means cerumen, if we use a technical term for it. And that's cool because that's a sticky trap for foreign bodies and it repels insects. So it actually keeps the ear canal clean. The three ossicles that we talked about here, they're known as the hammer, the anvil, and the stirrup, or the malleus, incus, and stapes. And you don't need to know those names. They are just three little bones, the smallest bones in the body. And when they vibrate, they bring the sound waves, which are actually pressure waves, and vibrate them right onto here, which is the beginning point of this cochlea here, which is the snail-looking thing. We'll do that in a minute. But one more structure is, because you got this middle ear, and the middle ear is basically closed from the outside world. And that's a problem, because like if you go out in an airplane, for example, your pressure changes quite rapidly on the outside. But this pressure here in the middle ear, how is that going to adapt? And if it doesn't adapt, you're going to get a different pressure on the inside and the outside. That's going to hurt the eardrum, I tell you that, from personal experience. Because the adaptation, the balancing out of the pressure is done by this eustachian tube. And the eustachian tube is a connection to the nose, the upper nose. And it balances out the pressure that way. Now in kids, the problem with kids is, the eustachian tube is not as steep, it's more horizontal. And when the eustachian tube is more horizontal, we get crap that's in the nose moving sometimes into the middle ear and giving us middle ear infections. That's why you tell a kid to blow the nose out and not get the snot going upward, because it actually does bring more stuff into the eustachian tube and potentially into the middle ear. That's kind of cool. And if you can't balance out the pressure, you got to push down and balance it out. It's because the eustachian tube is a little bit clogged. Sometimes it's not that patent, not that open. The word patent means open. All right, let's go to the next thing. Let's go to this weird looking stuff. So this is where it gets a little trippy. The inner ear consists of multiple fluid-filled channels that worm through the temporal bone. So let's look at that. We got one here. That's a channel. That's the cochlea. That's where we're going to hear. Then we got this here. That's the vestibule. And that's this bottom part here. This bottom, like up here, this bottom little bulgy thing. The vestibule actually has two. See, that's why I call it. It has an utricle and it has a saccule. It's not the same shade, huh? And then we also have three channels. You can see them here best. We got one here, we got one here, and we got one here. They're half channels, so they call them semicircular canals. And those channels are in all three directions. So the vestibule and the semicircular canals are going to help us with the organ of equilibrium. We're going to do that after we're going to figure out what's going on with this hearing stuff. So let's go through the hearing stuff a little bit. Oh, wait. This blue thing here, that's the bone carved out space, and that's filled with a fluid called perilymph. I know. Peri means around. Okay? On the inside, we have these brown looking things. And these brown looking things here, and going around, all the way around on the inside, those are actually membranes. And the membranes are filled with another fluid called endolymph. So we got a bony thing. The carved out bone has fluid in it. And then inside that bony thing, we got small little bags that carry another fluid called endolymph. They call the bony part the bony labyrinth, and the membranes, the membranous labyrinth. All right, let's go now to the cochlea. So the cochlea is a spiral, snail-looking thing about 3 centimeters in length. That's about an inch, more or less. And it winds around 2.5 times around its own axis. Yeah, it's a snail. When we look at the snail on the inside, when we take away the bony part on the outside, we actually see we have different chambers, because we got the bone, and then the membrane on the inside actually separates it in 3 chambers. We got one on top, if we take a square look out of it, one on the bottom, and then the goofy one looking in the middle. That's actually the membrane one that's sort of pushed in there in between the other 2. So we got a scala vestibuli, that's the superior looking one. And we got a scala tympani, that's the one on the inferior. That actually, we have to talk about this. We haven't talked about that yet. The window. So the scala vestibuli is where the last middle ear bone, the little ossicle, vibrates to. That's why that's called a stirrup, because it's got this plate down here and it pushes like the pressure waves, the sound waves or pressure waves. It pushes on it and it brings these waves on the inside here, and then the waves go through that lymph. They go all the way around, depending how far they get. So that's the scala vestibuli, and then on the bottom we got that scala tympani, and the scala tympani vibrates the sound waves out of another window. It just vibrates and it goes into air, so it doesn't go anywhere. It just bounces off into space, and that's the scala. That's the round window, and that's the end of this scala tympani. I know that's complicated. Now let's get to the kahuna though. The kahuna, where everything's going to happen, is in the scala media, and that's in the membranous labyrinth. We also call that the cochlear duct. Ooh, this is a nice picture. Or they call it the spiral organ of Corti. Look at that. Old names. So the organ of Corti then what that does, it transduces sound waves or pressure waves into nerve impulses. So how does it do that? So let's look at this picture. So we have, on the bottom, we have a membrane. They call it the basilar membrane or basilar membrane. And from there we have multiple different cells, but we got these cells that have hairs on them. And the hairs stick out. The hairs are actually cilia coming off of the cells. And they touch a gel structure, the gelatinous membrane on top. They call that the tectorial membrane. And so we have that all along the snail, all through that snail, in here, all along we have these receptors, thousands of these receptors in a row, right arranged there. And so now when a pressure waves comes in, and this is actually the snail a little bit, rolled out, so it's a little easier to see. So when a pressure wave comes in, or a sound wave comes in here, the sound wave travels through this upper channel, and then it actually also travels back to the lower channel. There's actually a place on top of the apex of the snail that the scala vestibuli and the scala tympani connect. That's called the helicotroma. Hold on, I did not show you that. That's right here, helicotroma, like helicopter. I know, it's on top. So now sound waves come in, and one more thing that we need to talk about is this channel narrows as it gets to the top. So it gets narrower as it gets to the apex. See, this is an uncoiled cochlea, so this is rolled out. So you see how there's a bigger distance here, and it gets shallower, a little shallower here. When we then look at, and so then all the receptors, all these are laid out all along here in the scala media, in the cochlear duct. When now sound waves come in, and depending on the pitch of the sound waves, the higher pitch the sound waves are longer and higher. So here, where the channel is larger and bigger, all of a sudden the sound wave will hit the bony wall, and when it's up here. When it hits the bony wall, it starts vibrating the scala media, and when it starts vibrating the scala media, those hairs start vibrating, and when those hairs start vibrating, we're gonna send the signal to the brain. So high-pitched ones that come in with a higher pressure wave will bounce off the bone sooner and carry over, Lower pitched ones, which have a shallower wave, will take a longer time till they hit the bone and then carry over and vibrate the scala media. So there you go. Essentially, hearing is vibrating hairs at a specific location, and then the nerve sends the signal. See, the nerve comes out of here and sends the signal to the temporal lobe, actually, and we get to the primary acoustic cortex, and that's where we hear. Coolio. I know, we'll do more in class to make it clear, but I hope this is sort of understandable. When we have hearing problems, we can actually, like in vision, we can figure out a little bit with what's going on with a tuning fork to see what the problem is. And we either have a mechanical hearing problem, which means the sound waves do not get to the organ of Corti, or we have a neural hearing problem, which means the organ of Corti does not translate the sound wave into a nerve impulse. So when we take a tuning fork and we put it in air and we can hear how well the sound waves travel to the ear, but we do not know if we have a conduction problem or we have a neural problem. We just know we hear or we don't hear as well on one side, or not at all. But then what we can do is we can take a tuning fork and put the tuning fork on a bone and vibrate the bone. And what happens then is the vibration doesn't go through air or the ossicles, it goes through the skull and it vibrates the right organ of Corti that way. And when you cannot hear anything when you put the tuning fork onto the bone, then you know your nerve don't work, because you take away the conduction, we change the conduction, the means of conduction from the air through the ear to the bone, from the bone to the ear. So that's described in the Weber and Rhine test, and we'll do some of that in lab, hopefully. Then we get to the organ of equilibrium. And what we have to do in that, if we need a balance, we basically need to pick up when we change the position of a head. And when we make a motion with the head, which can be actually with the body, it's the head in gravity, it's not the head on the body, it's the head in gravity. But when we move the head, we have a little starting of the motion, then we have a little stopping of the motion. And we have also hairs that can pick up that starting part, that acceleration of a motion, and the stopping part, the deceleration of the motion. And we got 5 different ones, because we have to code a few different acceleration, decelerations of the head. So we got some, the auricle and the saccule, they are sensing horizontal motions, sideways, and up and down motion, vertical motions. And then we got so that's the auricle, the saccule, those are the 2 in the vestibule. And then we got the semicircular canals, we saw those look sort of goofy. And what they do is they are in all different directions, and so they create angular motion. So that is when you spin around in a room, for example, around your own axis, that's the one that picks it up, right here, this one. And we can see that here. We can roll sideways, we can pitch up and down, or we can yawn left and right. So that's what these pick up. Now, how do they do that? How do they pick those up? Well, they're bending hair cells that send a nerve impulse, basically, or they stimulate a nerve impulse. So here, what we do have is we have the fluid filled area, and when we move around, the fluid moves with it. But if we now have an area within that fluid that's sort of a weighted thing, like here it's called a cupula, a weighted thing, and that weighted thing is a gel structure, has a little weight on it, and it goes around these hair cells. When we move, that weighted thing lags behind the motion, and it swings and it bends the hair cells, and when the hair cells bend, we fire a signal, and we'll feel that we motioned and we moved. So now the cool thing is, when you spin in a room and you keep spinning and you keep spinning, all of a sudden your spinning is normal, because after a lag period, that band will move back, because now it moves together with the fluid. The problem is then when you stop, then you get dizzy and you fall down. Because at that point, the fluid moves again and the thing lags behind big time. And of course, that's the dizzy feeling, which is fun as kids. And then we get older and it's like, not as fun. But that's how that works. So that's pretty neat, I think. And so, you can put some terminology on here. You could put on a crista ampullaris is the crest that houses the hair cells that are within dilations of the base of each semicircular canal, which is known as an ampulla. And then the cilia are covered in this cupula, that's the gel structure, and that's displaced when we move. When we look at the horizontal motions, we have these thing, this thing that happens in the utricle and the saccule. Their hair cells are actually weighted down by a membrane that has what's called otoliths on top. Or look at that, otoconia. But otoliths are little rocks. That's the term they use in the texts. And then with movement, same as rotational, just acceleration, deceleration of horizontal, like you're in a car and you start going fast, or up and down, vertical, you're in an elevator going up fast or so. That's when they lag behind with the weighted membrane. Same difference other than that. So the cool part is, we here with hair bending, we pick up acceleration, deceleration, motions with hair bendings, and last but not least, we're also going to pick up taste and smell chemicals with hairs. So on the tongue, and actually in the whole mouth, the palate too some, we have taste buds that pick up tastes. And we basically have chemicals that are suspended in some saliva, in some liquidy stuff, and the chemicals get trapped in here, in these little papillae on the tongue. And as they get trapped, they go down, and when they go down, they touch these little cells here, and they have hairs on it. And these are sensitive, these are microvilli, they're not cilia actually here, but these are sensitive to different chemicals. And in the tongue, in the mouth, we have tastes. We have 5 different tastes. We have sweet, sour, salty, bitter, and umami. And umami is this beefy, flavory MSG thing that makes stuff yummy. We just figured that one out a while ago, so if there's still some old textbook that just talk about 4, then that's why. Umami is a recent one. But what's interesting, we only pick up 5 of those, not more than that. So most of what we eat, the bouquet of odors of food, is to do with smell, not with taste. So when you got a stuffy nose, that's why it doesn't taste that great, because it's just picking up the tastes, and those are very crude and rudimentary. The tongue also, of course, picks up a lot of sensations, like from a mechanical touch sensations when we eat food. So it's not just taste of what matters in food. And then, of course, we have mucous serous glands around the area that flush the chemicals out, so we don't keep that taste in the mouth too long. But that brings me to smell, and that's the last one we talk about. And the smell mucous membrane lies in the upper nasal turbinates on each side of the nasal septum. That's the upper nose, top of the nose. It just lies up here, top of the nose. You got these cells that actually come down through the cribriform plate. Remember that? Cribriform plate, and there's the epithelial cells, and then the nerve cells reach down, and these cilia, these hairs again, pretty much, they're actually bipolar cells here. That's the second place we have bipolar cells. And they pick up volatile chemicals that are trapped in moisture. The airy stuff. And then once the specific odor receives it, we go up and we fire onto the olfactory bulb, and that sends the impulse to the olfactory cortex, and of course a lot of also to the limbic system. We can pick up thousands of these odor and chemicals, and it's actually a receptor question, so it's a shape question, which is kind of funny. That we can pick up so many, and of course we are not even good at it. Animals like dogs are a heck of better at it. So this is a very, very delicate sense. It's a very interesting sense. All right, so I think that concludes the nervous system. Hooray! And we learn hopefully a lot in it, and we'll move on to the next chapters. Thank you so much for paying attention.